All right, let's dive right into this explainer on exactly how our digital world is physically built and logically navigated. Every single time you send an email, stream a show, or load a web page, your data is traveling across a highly structured system. Today, we're going to act as digital architects, looking at the actual blueprints and the routing systems that make modern communication possible. Here's our roadmap for today. We're covering the foundations of network design, the basic topologies, advanced complex topologies, and finally, the postal system, otherwise known as IP addressing.
Let's kick things off with Part 1, the foundations of network design.
Before we look at the actual blueprints, we have to get one absolutely crucial distinction down: the difference between physical and logical topologies. Physical topology is exactly what it sounds like. It's the actual, tangible layout of the cables, the switches, the devices. Think of it as the asphalt in the intersections of a city. But logical topology, that's how the data actually moves across that network, regardless of where the cables are plugged in. It's the invisible traffic rules, like CSMA/CD in Ethernet, or token passing, that dictate exactly who gets to drive their data and when. Moving right along to Section 2, the basic topologies.
Imagine a single straight road. That's essentially your bus topology. All your devices share one main common cable, which we call a backbone. Data gets broadcast out to every single node, but only the intended recipient actually accepts it. And see those markers at the very ends? Those are terminators. They are absolutely essential because they absorb the signal and stop it from bouncing back and scrambling all the network traffic.
Now, the great thing about a bus setup is that it's incredibly cheap and super simple to wire up. But there is a massive downside. A single break anywhere in that main backbone cable will literally bring the entire network crashing down. Because of that major single point of failure, you're mostly only going to see this in older legacy setups, like early 10-base-2 Ethernet or your traditional cable TV distribution networks. Okay, now look at the massive shift in architecture here with the STAR topology. Instead of sharing a line, every single computer relies entirely on a dedicated point-to-point connection to a central device. That's usually a hub or a switch. Every piece of data has to pass through that exact center point. This setup is a real game changer because it provides fantastic fault isolation. If one cable breaks or a PC completely dies, it only affects that one specific device. The rest of the network just keeps humming along. It's so incredibly easy to manage and troubleshoot, which is exactly why it's the gold standard for virtually all modern Ethernet networks, from the Wi-Fi router in your living room to massive office LANs. The only catch, if that central switch fails, the whole network goes dark. Let's switch gears and look at the ring topology. This builds a continuous, closed circular loop where each device connects to exactly two neighbors. Data travels around this ring, usually using a very strict token passing system. Think of it like a talking stick in a group meeting. Only the computer holding the digital token is allowed to transmit data. This completely eliminates data collisions. So while this guarantees equal access for everybody on the loop and gives you highly predictable performance even under heavy loads, it shares that same critical weakness with the bus topology. Just one single cable break takes down the entire network. On top of that, just adding or removing a computer temporarily disrupts everything. Historically, this was huge in IBM token ring networks, and it is actually still used today in super high-speed SONET fiber optic rings for telecommunications.
All right, let's scale things up. Section 3, Advanced Complex Topologies.
Welcome to the full mesh topology. This is a highly redundant, almost bulletproof web where every single device has a direct, dedicated cable connecting it to every other device on the network. If one link fails, no problem at all. The data simply reroutes automatically down another path.
But check out the math on this because it is staggering. To figure out how many cables you need, you use the formula n times n-1 divided by 2. So for just 6 nodes, you need 15 separate connections. Imagine wiring in an office with 100 computers. You would be drowning in an absolute nightmare of 4,950 cables. Because of that astronomical cost and the sheer volume of cabling required, full mesh designs aren't something you'll ever see in a standard office. They are reserved exclusively for environments where supreme reliability is demanded, places where failure simply isn't an option. We're talking internet backbone routers, military networks, and critical infrastructure like power grids. For really large, practical networks, engineers use the tree topology. You can think of it kind of like an organizational chart for a company. It branches down hierarchically from a main root switch at the top, flows down through intermediate switches, and finally reaches the leaf nodes, which are your actual computers. It cleverly takes the star structure at each level and connects them with bus-like trunk connections. The best part about the tree topology is that it's wonderfully scalable. Need to add a new department or a computer lab? You literally just add another branch. It segments traffic beautifully. But it does carry a heavy risk. If that very top root switch dies, all the branches below it are instantly isolated from one another. Still, this is absolutely the go-to architecture for corporate headquarters and massive university campuses. Finally, for the absolute largest and most complex environments, we have the hybrid topology. This approach flexibly combines distinct layouts to get the best of all worlds. For instance, you might link up multiple independent star-wired buildings using a high-speed bus backbone. It gives you the ultimate customized design for enterprise networks. You get fault isolation, so a failure in one section doesn't break the others, and you can optimize performance for every single segment. The downside? Troubleshooting a hybrid network requires a deep, expert understanding of multiple overlapping architectures. You'll find this beast powering massive data centers and sprawling citywide networks. Now for the final piece of the puzzle, Section 4, the postal system, also known as IP addressing. So we've built the roads, but how do we actually send the mail? Enter the Internet Protocol address. An IP address is a unique numerical label assigned to every single device participating in a network. The most common version, the one you interact with every single day, is IPv4. It's a 32-bit address written out in what we call dotted decimal notation. That basically just means 4 numbers, each ranging from 0 to 255, separated by dots. A classic example you've probably seen is 192.168.1.10. Now, this seemingly simple string of numbers serves 2 absolutely critical purposes. First is identification. It uniquely identifies your specific host device on the network. And second is location. It acts as a logical map, giving routers the exact path they need to figure out how to forward your data to its final destination. To make this crystal clear, let's use a real-world postal analogy. Every network card has a hard-coded MAC address. Think of that MAC address as your actual first name. It's great for identifying you inside your own house on your local network. But if someone across the globe wants to send you a letter, your first name just isn't going to cut it. The IP address is your global street, city, and country address. It is the logical location that enables the entire world to route a packet right to your front door. As we wrap up our exploration of the digital blueprint, I want you to take a look at the device you're using right now. Ask yourself, what complex physical webs, whether it's star, mesh, or hybrid, and what incredibly precise logical IP addresses are working together this very second to keep you connected to the rest of the world? It is a vast, invisible infrastructure. And now, you know exactly how to read the map. Thanks for hanging out with me for this explainer, and keep exploring the hidden structures that power our world.